Okay, so let's go ahead and get started. So today we're going to look at more derivative rules. Okay, so as I did before, or as I did last class, I'm just going to write these down without proof, but I encourage you to look at the proofs. They're just straightforward applications of the definition of the derivative to get these rules. And again, we're going to assume that the functions that I write down are differentiable. So for example, in the following bullet points, f and g are differentiable functions of x. So the first rule is that the derivative with respect to x of f of x times g of x, this is going to be equal to f of x times the derivative of g of x with respect to x plus g of x times the derivative of f with respect to x. So this is called the product rule of differentiation. And the second rule is called the quotient rule. Okay, and this is kind of a long, nasty looking equation. But if you have the derivative of a quotient of differentiable functions, then this is, so derivative of f over g with respect to x is going to be g times the derivative of f minus f times the derivative of g, all divided by g squared. Okay, so that's the quotient rule. Okay. Now, to be honest, I forget this one all the time because I never use it. I always try to use the product rule when possible, together with what's known as the chain rule, which we'll cover after we do some examples of these. So, let me just pick some random problems to look at. So I guess this one is fine. So example, let's look at the derivative with respect to x of the function 3x squared times sine of x. Okay, so here we can split this function, this product here into two functions. So we could say, for example, that f of x is going to be the function 3x squared, and g of x is going to be the function sine of x. So then we see that this is a product of these functions. We know that both of these are differentiable. It's a simple polynomial, and we know that the sine function is differentiable. So then we can apply the product rule to find the derivative of this product. So what this is going to be, so it's going to be, say, 3x squared times the derivative with respect to x of sine x plus sine x times the derivative with respect to x of 3x squared. Okay. So what does this become? We have 3x squared, so the derivative of sine, if you recall from last time, is cosine. So it's times cosine of x. And then here we're going to have sine x times the derivative of this, And if we apply the power rule, we see it's going to be 2 times 3 times x to the power of 1. So the derivative of that is just going to be 6x. All right, so that is the answer, but it might appear different in your textbook. For example, it might look like we can always factor out everything that we can. I see a common factor of x and a common factor of 3, so I can factor that out. And then we would have so then 2 sine x. Right, we took a 3 out, a 3x from here, so we're left with just 2. And we took a 3x from there, so we're left with just x. Okay. So then this here would be the final answer. Any questions on that? Okay. So hopefully I can squeeze in frame here, so it looks like it goes over to here. Okay, so let's do the quotient rule now. So, oh, I almost forgot. This is only defined when g of x is non-zero. You have to always include those whenever you're using these rules. So I'm just going to pick a random problem from the book. Okay, so I want to know the derivative with respect to x of 3x minus 1 all over square root of x. Okay, so we can do this whenever x is not equal to 0, basically, because we just want to avoid division by 0. So with that assumption, x is non-zero, and so g of x is non-zero. We'll just make note that f of x is equal to 3x minus 1, and g of x is just square root of x. So being very careful when you apply this formula, because there's a lot of different terms. I like to, well, when I was learning math, I like to explicitly write out what the pieces are so that I can double check myself when I evaluate this formula. I can go back in and say, okay, g was there, f prime, so forth and so on. Just so if you want to be careful about it, I encourage you to actually explicitly write out f and g when you're using these complicated looking formulas. Okay, so what is the derivative of this? So it's going to be g, and I can reference what g is. So that's g times the derivative of f. So d dx of f. Hopefully you can read that. Okay, minus f hopefully you can read that. It looks a little blurry. Times the derivative of x. And this is all divided by g squared. Okay. Now, notice how this notation is a little bit cumbersome. Like, look at how complicated this is. So I just now remembered something that I used to do when I was learning math. That I'm going to pause on continuing here. I'm going to erase right here, and I'll show you how I used to do it to be extra careful. So give me a moment to erase that. And you'll be able to see it a little bit clearer. And I apologize if this is overkill for anyone and you're just able to just do it really fastly. I'd just like to show each step so that when you go back and look at your notes, you'll be able to piece together everything, even if you understand it right now. Okay. Okay, so what's the problem at hand? You want to find the derivative of that. So okay. So here is my solution as I would have done it as a student. I would say let f of x equals to 3x minus 1 and g of x equals to the square root of x. Okay, so I've clearly defined what these things are. And I would even use colors when I was a student. I would say, okay, this is f, and then maybe I'd use like yellow for g. This is g. Okay. So then now I'm going to find the derivatives of these pieces before plugging into that formula. So then f prime of x is equal to 3x, oh no, sorry. The derivative of this is just 3. Okay, so the derivative of f was easy to find. Okay, so then what about the derivative of g? Okay, so that was easy. We like a star there. And then now I need to find the derivative of g. So I would just note, maybe notice or note, g of x, which is the square root of x, is really like saying x to the power 1/2. So now that I have it written this way, I can see that I can apply the power rule of differentiation to get the derivative. So then g prime of x is equal to 1/2 times x to the power 1/2 minus 1. I just multiplied by the exponent and then decrease the exponent by 1. So what does this equal? 1/2 times x to the power minus 1/2. 1/2 minus 1 is negative 1/2. And this is like saying 1 over 2 square root of x. Because you have a negative exponent, you can put it in the denominator, the exponent becomes positive, and a exponent of 1/2 is the same thing as saying the square root. So now we have all of our pieces. So I'll just go ahead and write this over here again. So I'll do it in green. I don't know if you'll be able to see it, but the derivative of g is there. And then maybe in blue, the derivative of f is here. So now I have each piece that I need to plug into this formula. So then the derivative with respect to x of that thing up there, 3x minus 1 over root x, I can just plug in those pieces into the quotient rule. So then g, right, is the yellow thing up there. So g would be root x. Okay, there's my g, and I would even do this, with like yellow around it because it's the yellow one. And then f prime is 3. And I might even put blue around that to match up. And then we have minus f. This is 3x minus 1, so that's f. Okay. And then finally, we have g prime, which is in green. Okay, so g prime is that. This would be 1 over 2 root x. And that's in green. Two, by the way. And then we have g squared in the denominator. Yeah. And I'm just being like overly cautious right now, but just some techniques to maybe make use of when you get to really complicated expressions. Like, you need to plug in things there, but you need to figure out what those pieces are before you can plug it in to make sure of the final solution. So let's see what this becomes. I'm probably going to need some room here. So this is equal to 3 root x. And then we have minus that. So this would be, so maybe I can just say minus 3x minus 1 over 2 root x all over that square root, which is just x. So now we need to simplify this, and this is where if you struggled in algebra, you would probably have problems simplifying this. So what does this become? So I'm going to, I guess, combine the numerator of this ratio first. So this would be, multiply this by 2 root x over 2 root x. So you would get 6x minus 3x minus 1, no, plus 1, all over 2x root x. You see what I did there? Which, by the way, this simplifies to 3x plus 1 over 2x root x. So this numerator here is just combining these terms here. And then once you do that, you have a common denominator of 2 root x over x, so that's the same thing as dividing by x. So then this here, something like that, which you should always note that that thing's only going to exist when x is not equal to 0. Okay. So I'm going to pause the recording real fast and okay. So now that we briefly discussed the product and quotient rule, we're going to move to arguably the most important rule of differentiation. And this is section 2.4 from your textbook. And this rule is called the chain rule. Now, this rule is important for every major, math majors, physics majors, engineering majors, but as data science majors, this is important. Well, I'll just write it out. The chain rule, so this is an essential tool for deep learning. In particular, this thing called the back propagation algorithm. Essentially, and this is somewhat of an imprecise way of saying it, but I'll still say it. Deep learning is the modern version of machine learning. The concept of deep learning has been around for a very long time, but it wasn't until this back propagation algorithm was designed that it was actually feasible to do and to have machines learn computer vision, for example, or voice recognition. And the backbone of this algorithm is iterating through the chain rule. Because the way that neural networks work is that they're basically, a neural network, one way of thinking about it is a highly composite function. It's a function that's composite with other functions, which are composite on top of other functions. And through these compositions of functions, you can get very elaborate functions that can make predictions as to, you put in an X and it can make a prediction that that X that you put in was a deer, if it was like a picture or something. So that's really important for deep learning. This rule is essential for deep learning. And I actually, after class last time, I figured out a way to give a very simple single neural net lesson for you guys. Even though you just have Cal 1 derivative knowledge, I figured out a way that we can do this, and I'm pretty excited to show you that next week. Okay, so what is the chain rule? Well, it's basically this theorem. And this is the chain rule. So, okay, we're going to say that if U is equal, no, not U, sorry. If Y is equal to F of U, So f is a function of u. So if y is a differentiable function of u, right, so the variables for the function y are u's, not x's. So y is just some function of u, and it's a differentiable function of u. Okay, and u equals g of x is a differentiable function of x. So differentiable function x, then the composite function, say y equals to f of g of x, is differentiable with respect to x. I'll just like differentiable with respect to x. And the derivative is defined as follows. So dy dx, so y is a function of x in a composite form. The derivative of y with respect to x is equal to the derivative of y with respect to u times the derivative of u with respect to x. So dy dx is equal to dy du times du dx. Now remember that this is notation. These aren't actually ratios. You can kind of think of them that way, but these are, you haven't really gotten to it, but you can think of these as like changes in y, changes in u. These are not values you can just like divide out. And it's important to know. So like derivative of y with respect to x is, well, the rate of change in y with respect to x, right? So these are changes in quantities. That's what that's saying. Another way of writing it, so this is the main formula that I think of, but another way of writing it is as follows. So dx of the composite function f of g of x, so f is composed with g of x, is equal to f prime of g of x times g prime of x. Okay. So it seems rather technical, but it's really easy to implement in the calculate. So for example, we can look at, so find derivative with respect to x of the function square root of, say, 3x squared minus x plus 1. Okay. So here, we can identify this as a composite function. So for example, f composed with g, so f could be, so maybe I really want to emphasize this notation here, so I'm trying to think of the best way to do that. So I can probably squeeze it on this side. So we can like try to figure out how this looks with respect to this technical looking theorem. And then after we do that one time, then you'll see how to do it every time and you won't have to do this anymore. I just want to emphasize how this matches up, okay? So we can say that y, so what is the function y? Y is a function of u, so we can say that y is equal to the square root of u. And then g, oh no, u, sorry. U is equal to, say, 3x squared minus x plus 1. So notice that, and this is like, if we follow this notation right there, y is a function of u, I can also say that like this is like f of u. And then here, I can say that this is the function g of x. So that's f of u, that's g of x, y, u. Okay, hopefully the notation is not too confusing. Okay, so we want to find dy dx. Like this is like right here, f composed with g, right? So the way that we can do this is we can say, okay, let's find the derivative of this. So dy dx, so the derivative of y with respect to x is equal to the derivative of y with respect to u. So du, so what is y? It's the square root of u times du dx. So this is u. So then d dx of, hopefully I can fit it, 3x squared minus x plus 1. So what is the derivative of square root of u with respect to u? So you're treating u like a variable here. So this is the same thing as saying like the square root of x. What's the derivative of that? And we know what that's going to be. We just calculated it earlier. It's going to be 1 over 2 the square root of u. That is that. Okay? And then here, what is the derivative of this, where it's going to be 3x squared, no, sorry, why do I keep on doing that? It's going to be 6x minus 1. So that's the derivative of that with respect to x. Oh, not quite. I would have to literally plug in u. This is u. I don't have room for it, but you would plug it in and then you would have the full derivative with respect to x. Okay. So another way of thinking about this here, so this was using dy, this is using y and u, this version. So now let's use this version here. This other way of using notation. It's just different notation. Same version, different notation. So this derivative here. So what's the outside function? Right? The outside function is f, right? What is f? Square root of u, right? So what's the derivative of the outside? Well, I'll just write out this a little bit more detailed. So this is like saying 3x x squared minus x plus 1 all to the power 1/2, right? This is the same thing, right? So what's the derivative of the outside function? Well, it's like taking that, like whatever was in there is a variable. So it's 1/2 times the front, so 1/2 times the front. And then whatever is here to this power minus 1. So 1/2 minus 1 is minus 1/2. So that's f prime, that's the derivative of the outside, times the derivative of the inside. What's the derivative of the inside? So just ignore everything else. What's the derivative of the inside? It's 6x minus 1. So then this simplifies to 6x minus 1 all over 2 times the square root of 3x squared minus x plus 1. And you see, if we would have plugged in what u was in terms of x, this and this would have matched up. Derivative of the outside function times the derivative of the inside function. That's all it is. And there's just two different ways of writing it. Like y is the outside function, right? So then derivative of the outside with respect to x is derivative of the outside with respect to u, the inside, times the derivative of the inside with respect to x. Are there any questions on that? We should probably do a few more examples. So let's do like an easy one. So let's say find, let's say the derivative with respect to x of the function sine 2x. So here, what would the outside function be? So if f of u is equal to sine u, well, no, I'll go ahead and say this. I'll just use x's. It might make it easier. So if that's f of x, and here's g of x, then we see that this derivative here that we're searching for that's equal to the derivative of f composed of g of x. So then, as before, it's the derivative of the outside function, which is f. So what's the derivative of sine? It's cosine. Okay. Actually, I need to be careful here. I should have kept this u. Okay. So then the derivative of the outside function with respect to u is that times the derivative of the inside function, which is that. So then we see that this is going to be 2 times cosine, and then plug back in what u was. U was 2x, so there. Again, it's the derivative of the outside times the derivative of the inside. Okay. So let me pause the video real fast, clean off. Okay, so let's go ahead and look at the solutions. So solution here. So dy dx. So the outside function would be just like x cubed or u cubed, right? So then this would be 3 times the inside to the power minus 2 times the derivative of the inside, which is just 2. This would be 6, 2x minus 7, all squared. If you worked out the derivative of the inside, you'd see it. That one, I didn't do everything I was doing prior, but that is the answer. Derivative of the outside times the derivative of the inside. So then here, so dy dx. So the derivative of the outside, so the derivative of cosine u is negative sine u. So negative sine of u, and u is 4x squared. And then times the derivative of the inside, so the derivative of u with respect to x, it's going to be 8x. So if you rearrange this, we'll have negative 8x times sine of 4x squared. Okay. So now here, this is an example where the quotient rule, this is just why I don't remember the quotient rule, because whenever I see a ratio like this, I will convert it into a chain rule problem together with maybe like a product rule, maybe. So just note that this is also the same as saying x minus 2 to the power minus 1, right? So then you can think of like f of u is just u to the minus 1, and g of x is just equal to x minus 2. And just remember that that whole function there is u. So now we can apply the chain rule. So dy dx, so the derivative of the outside is like derivative of that, right? So it's going to be minus 1 times u. So u is x minus 2 to the power minus 2 times the derivative of the inside, which is 1. So if you simplify this out, you get negative 1 over x minus 2. Okay. So what this is saying in ways like, so I should probably note a little bit behind the intuition behind the chain rule. And that's that if you have some composite function here, and we discussed that the derivative of a function tells you information about the rate of change, instantaneous rate of change at a point. So the derivative of the composites is really telling you as g of x changes, how much does that rate of change affect the rate of change of f? That's what we're doing. When we calculate these functions are telling us how, when g of x changes, how does f change when f is composed with g? So maybe I can just say like how do changes in X affect G, which in turn affects the changes in F. That's what we're learning when we take the derivative of a composite. Right? If you just for a standard function, it isn't. If you're treating a function as a composite function, you're really looking at how changes in X, which the outside function isn't necessarily a function of, how does that change the output? Okay. So we pause the video again.